Hello students, welcome back. In this lecture, we'll be studying about two theorems which are important in the circuit theory. One is the initial value theorem, and second is the final value theorem. So let's start with the initial value theorem. We know that the Laplace of a function d by dt of f of t is equal to s fs minus f of 0. We also know that the Laplace of any given function. So we also know that the Laplace of any given function, for example, the function is this, is equal to the integral from 0 to infinity of the function. Function is d over dt of ft e power of minus st dt, which is same as this, LHS being same. So is equal to s fs minus f of 0. Now taking the limit s tending to infinity and putting this in the above equation, you know that as s tends to infinity, e power of minus st will tend to 0. So this would mean that for s tending to infinity, for the function e power of minus st, it will tend to 0. So therefore, the whole of this expression will become as 0. So therefore, this Laplace of d by t of ft, which is nothing but this, will tend to become as 0. So 0 is equal to limit s tending to infinity of s fs minus f of 0. Now, which can also be written as, since f of 0 being constant, so therefore we can also say that f of 0 is nothing but a limit s tending to infinity of s into f of s. And f of t can also be written as f of t for t tending to 0. So therefore, I can write f of t for t tending to 0 is nothing but a limit s tending to infinity of s into f of s. And therefore, this expression is called as the initial value theorem. Now, similarly, let's take up the case of a final value theorem. Again, we can start from the same statement that we know the Laplace of a differential of equation. So for the purpose of elaboration, you can start with the same thing that we know that the Laplace of d over dt of f of t is equal to s f of s minus f of 0. But we also know that the Laplace of a function, we also know that the Laplace of a function is nothing but the integral of the function e power of minus st dt. So therefore, we can say that the integral of 0 to infinity of d over dt of the function ft into e power of minus st dt will be equal to the s f of s minus f of 0. Now taking the limits, taking as s tending to 0 would mean, if you put s is equal to 0, so this means for s tending to 0, so e power of minus st will be equal to 1. So this being 1 and the integral of a differential of a function is equal to the function itself. So therefore you can say that the integral of the differential of the function times 1 into dt is nothing but f of t, limits going from 0 to infinity. So therefore what do you see that from these equations, that is this equation and this equation are both same. So putting the value, that means I can write, so f of t for t tending from 0 to infinity is equal to limit s tending to 0 of s of fs minus f of 0. And the LHS being, if you put the limits, so you'll get f of infinity minus f of 0 is equal to limit s tending to 0, s tending to 0 of s fs minus f of 0. So as you can see, this being constant, so therefore you can these will get cancelled out, so both being constants. So therefore what we have is f of infinity is equal to limit s tending to 0 of s into f of s. Now from here, what do you see? That this f of infinity is nothing but ft for t tending to infinity. So this can be written as equal to f of t for limit t tending to infinity is equal to limit s tending to 0 of s into f of s. So this is my final value theorem. So let me uh, highlight this, and this is my final value theorem. These both the theorems will have a lot of applications in the solution of the circuits, especially in the S domain using the Laplace. So we will see some of the examples, the applications of the initial value theorem and the final value theorem in the next video. So till then, see you.